Good afternoon. Welcome to NPTEL project on econometric modeling. This is Rudra Pradhan here. Today we will discuss bivariate econometric modeling, that is with respect to regression analysis. In my last lecture we have discussed the entire structure of bivariate econometric modeling. So, basically it is divided into two parts. First part associate with the association between two variables, and in the second case we like to know the association along with the causal relationship. So, now in the first case there are several techniques: variance, covariance and correlation, and other sides there is a technique called regression. The difference is that in the first case, particularly with respect to variance, covariance and correlation, the objective is to measure the degree of association between the two variables. However, in the case of regression, we are interested for two things: first, the association between two variables, and second, the cause and effect relationship between two variables. So, basically bivariate econometric modeling divided into two parts, and that is with respect to degree of association, and second case its causal relation. Okay. So, we have standard techniques called as a variance, covariance and correlation. Here the standard technique is called as regression. So, now the starting point of this particular structure is that the system must have two variables. Okay. So, let us take two variables here. X represents x1 up to xn and y represents y1 up to yn. All right. So, now variance, covariance in fact very similar. Variance means we have to track the association with the same variable. For instance, we have to correlate with x upon x or y upon y. Okay. So, this is what it is called as a variance. So, now if we correlate x y or y x, then it is called as a covariance. Okay. Now, similarly, if we integrate x with y or y with x, then it is also called as a correlation. Yes, there is a small difference between covariance and correlation, but the objective of the particular study is very much similar, because we try to know the degree of association between the two variables. So, here the difference is only with respect to its mathematics only, nothing else. So, now in the case of regressions, we like to know the cause and effect relationship between the two variables. In my last lecture, we have discussed the detailed structure and status of covariance and correlation. However, we have not discussed anything about the regression. So, today we will discuss detail about regression, and we have to compare how it is different, or you can say advanced to variance, covariance and correlations. One thing is very clear: regression, you can say, very much depend on the variance, covariance and correlation. Until unless you have complete knowledge on variance, covariance, correlation, you cannot go for regression technique. Let me explain what is all about regression. Okay. So, now I have already discussed the structures bivariate econometric modeling. So, this is here association rule and this is here causality rule. Okay. So, now we will take the case of causality. So, now causality is nothing but it is technique called as a regression. Okay. So, now what is first question is what is all about regression? Regression is to predict or forecast a particular variable with respect to a given variable. In other words, it is the average association between two variables, keeping in mind two objectives. First objective, degree of association between the two variables, and second objective is to know cause and effect relationship between the two. So, that means if there are two variables, whether x causes y or y causes x. In fact, in the time series modeling, we have very interesting component called Granger causality. So, there are three different options. If x causes y and vice versa is not true, it is called as a unidirectional causality. Again, y causes x and not vice versa, then again it is called as a unidirectional causality. If x causes y and y causes x, then it is called as a bidirectional causality. However, we are not going detail about the time series modeling right now. We will discuss detail in the later part. So, in the meantime, we have to discuss what is the entire structure of regression. Means we like to know what is the basics of regression modeling. Okay. So, now regression is the average relationship between two variables. So, now the starting point of the game must have two variables. So, let us take two variables here. So, now regression can be obtained if there are two variables, say y and x. So, now if there are two variables, so then we are very much interested for cause and effect. So, that means there are two different situations here, y on x and x on y. Okay. So, now let us start with the y on x, then here this sides x on y. So, this is the component y on x is called as a regression line y on x, and x on y means it is a regression line from x to y. Okay. So, now if it is y on x or x on y, how is the setup or structures? So, let us start with here. If it is y on x, so what is the shape of regressions? The shape of regression is simply mathematically we can represent y minus y bar is equal to byx into x minus x bars. Okay. In the case of x on y, the regression equation is like this: x minus x bar equal to bxy upon y minus y bars. Okay. So, now certain things here you have to very clear. First thing, we know x is a variable, first variables. This is x is the first variable, okay, and y is the second variables. So, now I have not mentioned whether first variable means may be dependent, it may be independent. Second variable, it may be dependent, it may be dependent. Now, if I will say y on x, then obviously it is y dependent and x independent. The moment I will say x on y, then obviously it is x dependent and y independent. Okay. So, now x and y are two variables, x bars the average of x, okay, mean of x, then y bar is nothing but average of y. Okay. So, now we get to know y bar, x bar, then we have no idea about byx and bxy. So, byx represents a regression coefficient, it is represented as regression coefficients on y to x, okay. So, this is for byx. Similarly, we have bxy represents regression on regression coefficients on x y. So, this leads to here only. Okay. So, now the situation is very clear. So, we have two regression coefficients. First is x on y and second is y on x. So, now if it is x on y, the regression equation is x minus x bar into bxy into y minus y bar, and if it is y on x, then y minus y bar equal to byx into x minus x bar. So, there are two regression lines. So, obviously, we have two regression equations. So, now we like to know what is the structure and setup of byx and bxy. Okay, bxy is a mathematical coefficient, it is called as a regression coefficient, and bxy also regression coefficient from x to y, and for byx it is y to x. So, now we like to know what is exactly byx and what is exactly bxy. So, now that means we like to know what is the mathematics or statistics inside bxy and byx. Let me highlight here what is all about this issue. So, now let us start with the first one equation, y minus y bar is equal to byx into x minus x bar. So, this is regression on y upon x, okay, y upon x. So, now here byx represents r sigma y by sigma x. What is r here? So, r here represents correlation coefficient, r represent here correlation coefficient, okay, and sigma y represents standard deviation of x variables, okay. Then sigma x represents standard deviation of y. This is standard deviation of x, and this is standard deviation of y, okay. So, now byx obviously we have already represent, this is regression coefficients of y on x, alright. So, now what is r? So, in the last lecture we have discussed what is r. R is basically correlation coefficient, which is again derived through proper structures. So, now here this is this is first equation, this is second equation. Now, third is r equal to covariance of x y by sigma x into sigma y. This is conditional equation third, okay. So, now we have the original regression equation is y minus y bar equal to byx into x minus x bar, followed by bxy equal to r upon sigma y by sigma x, and again r equal to covariance of xy by sigma x and sigma y. So, now we like to know what is sigma x, what is sigma y, and what is covariance of xy. In fact, we have already discussed all these details. So, now sigma x is nothing but summation x minus x bar whole square divided by n, and sigma y represents summation y minus y bar whole square divided by n, okay. So, now we covariance. So, covariance of x upon y is equal to summation xy by n, okay. It is nothing but summation x minus x bar into y minus y bar divided by n, okay. So, this is the regression coefficient, this is correlation coefficient, this is standard deviation of x, this is standard deviation of y, and this is covariance of x y. So, now if we summarize all these details, then obviously ultimately byx is nothing but covariance of xy by sigma x into sigma y, alright, into sigma y by sigma x. So, now sigma y cancel. So, it is nothing but covariance of x upon y divided by sigma square x, that is nothing but variance of x. So, now this covariance of xy basically its covariance of xy is nothing but summation x minus x bar into y minus y bar divided by n. Okay. So, now again Byx is equal to summation x minus x bar into y minus y bar by sigma square x, sigma square x. Okay, sigma square x. So, it is sometimes written as summation xy by summation x square. This is divided by n. So, obviously summation xy by n cancel. At the moment you will take sigma square, because sigma square equal to summation x square by n. Okay, so summation x square by n. All right, that means standard deviation of x is nothing but summation x square by n. All right. So, now this is Byx. So, now if you will simplify, then it is nothing but y minus y bar equal to summation xy by summation x square into x minus x bar. Okay. So, this is the question of y to x regression equation. So, now come down to other part of this problem. So, that is x on y. Okay. So, now for x on y, then the regression equation is nothing but x minus x bar is equal to Vxy into y minus y bar. So, as usual Vxy is equal to r sigma x upon sigma y, r sigma x upon sigma y. So, now it is nothing but covariance of x upon y by sigma x into sigma y multiplied by sigma x by sigma y. So, sigma x cancel, ultimately covariance of xy divided by sigma square y. So, now if we further simplify, then it is something summation xy by summation y squares. All right. So, this is the final coefficient for Bxy. So, ultimately regression equation will be x minus x bar is equal to summation xy by summation y square into y minus y bar. So, this is the second equation on x on y. Yes. So, we have two variables. So, corresponding to two variables y and x, we have two regression equations, y on x and x on y. For y on x, the regression equation is y minus y bar into Byx into x minus x bar, and for x on y, it is nothing but x minus x bar into equal to Bxy upon y minus y bar. So, now Byx and Bxy is the regression coefficients. So, now we have to see how these two regression coefficients are integrated to each other and how it is very useful, or you can say very structured in the bivariate econometric modeling. So, let me explain here. There are various properties here which associated with the regression coefficient, correlation coefficients, covariance and variance. Ultimately, in this bivariate data analysis or bivariate econometric modeling. So, we are very much interested about variance, covariance, correlations and regression. Okay. So, now we have two series y minus y bar equal to Byx into x minus x bar, and another side x minus x bar equal to Bxy upon y minus y bar. Okay. So, now this is equation 1, this is equation 2. So, now we like to know how they are integrated to each others. So, that means, is there any relationship between these two equations or two regression coefficients, and how these two regression coefficients are integrated with the correlation coefficients, that too variance, covariance and its, you can say, structure. So, now let us start with here Bxy. So, one standard property is that the geometric mean of two regression coefficient is equal to correlation coefficient. So, that is what is geometric mean. So, now Byx into Bxy, for these two coefficients regression coefficient will be like this 0.5. Alright. So, what is Byx and what is Bxy? It is already mentioned. So, Byx is nothing but r sigma y by sigma x multiplied by r sigma x upon sigma y. So, sigma x cancel, sigma y cancel, this is to the power 0.5. So, it is simply r squares upon square root. So, this means r. So, now the physical interpretation is that the geometric mean of two regression coefficient is the correlation coefficient. So, that means if we have two regression coefficients, then we can get to know the correlation coefficient, that is simply the geometric mean of Byx and Bxy. Alright. So, now this is second property. The arithmetic mean of two regression coefficient is greater than two correlation coefficient. What is arithmetic means? Now, for arithmetic mean Bxy and Byx is nothing but Bxy plus Byx greater than equal to correlation coefficient. Okay. So, now how is that structures? So, it is nothing but r sigma x by sigma y plus r sigma y by sigma x greater than equal to 2r. Okay. So, now r cancel. So, sigma square x plus sigma square y greater than equal to 2 sigma x into sigma y. So, this implies sigma x minus sigma y whole square should be greater than equal to 0. So, it is meaningful statement. So, that means we can justify that the arithmetic mean of two regression coefficient should be always greater than equal to correlation coefficient. By any chance, it cannot be less than that. Alright. So, this is the second issue of the association between regression coefficients and correlation coefficients. Third property here. You know, r depends upon Byx and Bxy. Alright. So, correlation coefficient simply represents, or you can say, functional association between Byx and Bxy. So, now it is a very interesting. If r greater than 0, then Byx obviously greater than 0, Bxy greater than 0. So, that means for if Byx and Bxy positive, then r must be positive. Then if r less than 0, then Byx less than 0, Bxy less than 0. Okay? Or if r equal to 0, then Byx, or you can say Bxy is equal to 0. So, that means both regression coefficients and correlation coefficients are usually same sign. By any chance, it cannot be different. For instance, if regression coefficients are negative, then obviously correlation coefficient will be negative, because it is the geometric mean of the two. So, obviously both should be positive, so that we will get the positive correlation coefficient, and both should be negative to get the negative correlation. So, in one instance Bxy positive, and in the other instance Bxy should be positive. It cannot be other way around. So, this is how this third property is all about, between regression coefficients and correlation coefficients. So, now you must be very much concerned about this, the coefficient of correlation and the coefficients of regressions. So, now we have already mentioned that correlation coefficient always lies between -1 and +1s. Alright. So, now obviously r square lies between 0 to 1. Okay. So, this is correlation coefficient and this is the square of correlation coefficient. In fact, in the regression analysis, we will go deep into regression, obviously the R-square component is a very important factors, means it has lots of beautiness. So we will discuss detail what is all about R-square and how it is very useful for entire regression issues. So in the meantime, I like to know it is simply R-square, that means square of correlation coefficient. And if we go into deep, then the R-square represented as a coefficient of determination, and that is the measure of goodness fit. In the first lectures, when I mentioned about the structure of econometric modeling, I have discussed the entire setup. So how you start with econometric modeling and how you have to end with econometric modeling. In the very beginning, I have mentioned the first starting point is to define the problem, that you have to borrow from the theory. Then you have to transport the theory into mathematical form of the model. Then you have to transport the mathematical form of the model to statistical form of the model. Then we have to investigate that models, and for that you need to have informations, that is what we call data. So the moment you have data, then you have to apply the statistical techniques, tools, or you can say computational process, and get the estimated model. So now once you have estimated model in your front, then obviously the first assignment is to check the reliability before you like to go for forecasting or other issues. So now I clearly mentioned during that times that so far as the reliability check is concerned, we have three different specifications, three different tests, that is you can say goodness fit test, then specification test, and out of sample prediction test. And goodness fit test is one of the issue here only. So now what we are talking about R-square is nothing but the goodness fit test. So the goodness fit of that particular model depends upon the value of R-square. If the R-square value is very close to 1, then obviously the fit of the model is better. If the R-square value is close to 0, then the model cannot be better fitted. That means if the goodness fit is not reliable, so it cannot give any indication, positive indication, then obviously we cannot go for forecasting. That means we have to go back to your second stage. So the way we have structure or given the detailed structure about the flowchart. So now accordingly we have to proceed. So now by any chance if R-square is close to 1, then that means model is reliable, then you can go for forecasting, and that is you can say observe, or that can be done with the basis of only goodness fit test. So now here the point is that if R is in between -2 to 1, then obviously coefficient determinants limit is 0 to 1. So now if the value of correlation coefficient is -1, it is positive, means perfectly negatively associated with each other, and if it is equal to 1, then it is positively associated to each other, and that is perfect positive correlation, and this is perfect negative correlation. So in between 0 must be there. So 0 means no correlation between the two. So that means if the R value is 0, then obviously then the causality factor will not come into the picture, because if you will take any regression equations y on x or x on y, then obviously byx and bxy is the factors. So the moment you have a R coefficient 0, then obviously the entire issue byx and bxy also 0. So as a result, so by means regression equation y on x and x on y cannot be observed. Means it from correlation coefficient itself, it will give indication whether there is any cause and effect relationship, because it is the essential point whether you have to proceed further. That means if you are starting from the variance, covariance, correlation and regression, then it's just like a step by step process. So now if the correlation gives 0 result, then obviously no point to go for regression. The reason is that because regression is the advanced technique, it is very time taking and also mathematically very complex. So the moment you will get R equal to 0, then you can stop there. No point to discuss about the cause and effect relationship, because the relation itself is no meaning at all. So now if the correlation coefficient -1 to 1, then obviously coefficient of determination 0 to 1. So now so accordingly the goodness of fit will give the forecasting results. If it is close to 1, then it is better forecasted. If it is close to 0, then there is no question of forecasting, but if it is close to 0, then it is less reliable for forecasting. So now corresponding this particular setup, so we have another property is associated with regression coefficient and correlation coefficient. Structure is that here we know in the correlation structures, the correlations is a very symmetric in nature. So that means ryx equal to rxy. For instance, like this, we have two variables x and y. So that means we can correlate x upon y, or we can correlate y upon x. If we correlate x on y, it is called as a rxy, and if we correlate y on xy x, then it is called as a ryx. So that means the fundamental theorem is that rxy is equal to ryx. So that means it is simply symmetric in nature. It is simply symmetric in nature. Okay. And one of the other important point is that rxy is equal to ruv. U and v are another variables which is a other way representation of xy. For instance, u can be x minus a by h and v can be x minus b by k. So that means it is represented as the regression coefficient is independent of change of origin and scale. However, in the case of regression, it is not the issue. In the case of regression, it is change of origin but not the scale. The reason is that Byx is simply summation xy by summation y squares. Okay. So now if x represents here x minus x bar, and y represents here y minus y bar, and y square represents x minus x bar into y minus x into x minus, so y minus y bar into y minus y bar. Okay. So now if we will simplify here, then x minus x equal to hu plus a, and here b equal to y minus b, in fact y equal to kv plus b. So now x minus x bar is nothing but h into u minus u bar, and y minus y bar represents k into y minus v minus v bars. Okay. So obviously, so now if we simplify this, then summation xy is nothing but h into k summation uv divided by summation u square, means it is simply a k square into sigma summation v squares. Okay. So now this k cancel, then ultimately we have the factor h by k into summation uv by summation v squares. So that means it is clear cut indication is that regression coefficient is independent of origin but not the scale. Similarly, we can also you can make a verification for bxy. So the point is that correlation coefficient is independent of change of origin and scale, while regression coefficient is change of origin but not the scale. All right. So this is the case of regression issue and correlation issue. So now there is another point you can here and note down on this. When r equal to 0, then obviously the two regression lines are perpendicular to each others. Okay. So if r equal to 1, means if the correlation coefficient is equal to 1, then it means two lines are coincide. So that means if r equal to plus minus 1, then two regression equations are usually different, and there is a exact relationship between the two. If regression coefficients are not plus minus 1 or it is equal to 0, then obviously there is no relationship between the two. So that means there are three different situations altogether. If plus minus 1, then there is a perfect relationship, perfect association between the two. If it is less than that, then there is a relation, but it is not perfectly related to each other. However, if it is equal to 0, then there is no question of association, and also there is no question of causality. So this is the basic background of the regression analysis. So now we will explain with a suitable examples here. So how it is exactly structured so far as a regression equation is concerned. Let me take an example here. This is x series and this is y series. Okay. So x represents 71, then this is 68, then 66, then 67, then 70, 71, 70, 73, 72, 65, then 66. So 1, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that means here n equal to 11. Okay. So now if you make sum, then this is sum x equal to 759. So obviously x bar is equal to 759 divided by 11, which is nothing but 69. Alright. So now come to y structure. Y for 71, y is 69, for 68, y is 64, then for 66 it is 65, then it is for 67 it is 63, then 65, then this is 62, 65, 64, then 66, 59, then 62. So obviously n is here 11, because in the very beginning I have mentioned if we will go for variance, covariance, correlation and regression, the essential condition is that the sample observations must be same and unique. If the sample observations are not same, then you cannot make any association, or you cannot correlate, you cannot regress, or you cannot covariate. This is not the case when we will go for univariate setup. Within this particular structure, for instance, within this particular structure like this, we are just this is x within the system and this is y within the system. We are doing just our assignment y to x or x to y, either to regress or you can say to correlate. But this is what bivariate. Within the bivariate, if we are interested about x or we are interested about y, then there is no point. If this particular structure we will call it a n1 and this particular structure sample observation we will call it n2, then there is no point n1 should be exactly equal to n2. Okay. But if we will correlate between these two, in that case it is mandatory n1 should be equal to n2, but in this case, this particular case and this particular case, n should not be exactly equal to 2. So that means for univariate analysis, any univariate statistics, if you look, there is no point or there is no question about the sample observation uniformity, because the sample sample observation within the system represents the structure of univariate and bivariate and you can say multivariate. Our objective is completely different in the case of bivariate or multivariate. We just like to know how they are related to each other, and for that we need to have you can say information about the univariate statistics. Now within this setup, if you are looking for univariate statistic of a particular variable, then this is completely different. Now for another variable, the univariate statistic is completely different. That means altogether they are independent. But when you like to integrate each other with respect to covariance, correlation, regression, that time this whole unit should be very similar in nature. In the first case it is not mandatory, but in the second case it should be mandatory. Yes, there is a certain issue here. Of course, if we have x1, if we have x variable and y variable, I will say here you can say 1, 2, 3, 4, 5 up to say 10 observation. Another case we have 1, 2, 3, 4, 5, 6 up to you can say 8. So now the observations 6, 7 or you can say take this is 8. Okay. So now this is 8. So now what we have to do in that case, this is so far as univariate statistic is concerned, you can do analysis here, we can do analysis here. But when we will apply bivariate modeling here, then in that case the system is totally inconsistent, because this is the sample observation 8 and this is the sample observation of 10. So now this is nothing but inconsistency. So to solve this particular problem or to handle this particular issue, so what you have to do, we have to artificially create a uniform sampling. So that means either you can reduce the sample size or increase the sample size to 10, means 10 is already there for x, but in the case of y it is not there. So it is only 8. So we can extend 9 and 10 further. Okay, you have to extend 9 and 10 further. For that, either you have to explore where the information is available. If it is so, then your task is very easy, you can go ahead. But sometimes in the real world business, you may not have a information, but there is a standard mathematical technique through which you can fill that gap also. Here the one of the standard technique is called as interpolation and extrapolations. If you apply interpolation and extrapolation, then the sample unit 8 can be extended to 10. So in that case, you will get the uniformity in the structures. Then of course you can go ahead with the solutions. So, but every time you can apply interpolation and extrapolation. However, there is a certain problems associated with the interpolation and extrapolation. It can solve your problem. You can get the model best fitted. You can go for forecasting. You can go for anything, etc. But it will affect the reliability part of the model. So the moment you will go for interpolation and extrapolation to enhance the sample size or to get the uniformity in the sample, then one of the standard problem you can face is that called as autocorrelation, which is very complex, very serious and very interesting also. We will discuss in detail when we go for the autocorrelation modeling. So right now it is not issue here. So we just to know, and in the first hand we just to know how you have to solve this particular problem. Later on, when there is a additional problem or additional complexity, so far as the reliability check is concerned, that time we have some other tricks how you have to eradicate that problem. So we will discuss detail when we will go for that. Okay. So in the meantime, we have two observations. So x and y, x contains this much of information, y contains this much of information. So now in the first hand, sample observations are similar. So that means we can proceed further for the analysis. So there is no issue at all. In fact, sometimes when there is series of observations, this is 11, okay, by look we can say that there is inconsistent, and there are two variables only, then you can say that there is inconsistent. But when there is a multiple variables and multiple sample points, that time it is very difficult to observe. Yes, we have standard softwares, so we just enter the data, then you cross check it for all these variables. The moment you will put the descriptive statistics, so it will give you indication what is the observation n for all the variables and what is the mean of all the variables, what is a standard deviation, variance, all these you can say descriptive statistic, it will give you in details. So now with the available information x and y, so we have to we need to find out x squares, we need to find out y squares, we need to find out x y, then we have to proceed for the regression coefficient. Yes, to simplify further or the structure because of its simplicity, we can go for small x square, small y square and small x y. So here small x square is represented as some x minus x bar whole squares, and small y square represents y minus y bar whole squares. Okay. So that means, so here x bar is 69 here. So corresponding to this y, summation y is equal to 704. So n is 11. So obviously y bar equal to 704 by 11. So which is nothing but 64. So now if we transfer it, then every item has to be transferred into x minus x bar. So that means for first case it should be x minus you can say 69. So now if we transfer, then this structure will come to minus 1, minus 3, minus 2, then 1, 2, 1, 4, 3, minus 4, minus 3. So, similarly, in the second case, this is in fact x, okay. This is in fact x. So, obviously, we will go for x square and y square. So, for y it is nothing but 5, 0, 1, minus 1, 1, minus 2, 1, 0, 2, minus 5, then minus 2. All right. Now, this is x deviation format and y deviation format. So, now we need xy. So, xy of course, it is 10, then 0, minus 3, then 2, 1, minus 4, then 1, 0, then 6, then 20, then 6. Okay. So, similarly, you will get x square and you will get y square. X square represents 4, 1, 9, 4, 1, 4, 1, 16, then 9, then 16, then 9. Okay. Then corresponding y, we have y square 25, 0, 1, 1, 1, 4, 1, 0, 4, 25, 4. Okay. So, now we have x square, we have y square and we have xy. Of course, it is in deviation format. So, now summation xy is equal to here 39, then summation x square is equal to here 74 and summation y square is here 66. Okay. So, now we have to see how is the regression coefficient, how is the correlation coefficient. Okay. So, now given information with detail about its statistics, univariate statistics and bivariate statistics, that is with respect to variance and covariance, we have to proceed further for regression and also its correlation coefficient. So, now we have two different equations, y minus y bar equal to byx into x minus x bar, and other side x minus x bar is equal to bxy into y minus y bar. All right. So, now first of all we calculate what is byx. Byx equal to summation xy y. Okay, we can start with the covariance of xy by sigma x into sigma y, which is nothing but covariance of covariance of this is sigma y by sigma x, covariance of xy divided by sigma x into sigma y by sigma x. So, sigma y cancel. So, covariance of xy by sigma square x. All right. So, which is nothing but, we will simplify, it is nothing but n summation xy minus summation x into summation y divided by n summation x square minus sum x whole squares. Okay. If we will further simplify, then it is something summation xy by summation x square. So, that means summation xy is here, summation xy is here 39. So, 39 divided by summation x square is 74 years. So, this is what the regression coefficient. All right. So, now your equation will be y minus y bar is equal to 74 into x minus x bar. In other words, y minus y bar is here 64 is equal to 39 by 74, 39 by 74 into x minus x bar, that is 69, that is 69. So, now if we will simplify, then this will be simply in the format of y equal to alpha plus beta x, alpha plus beta x, alpha is and beta are supporting component. Similarly, in the case of x minus x bar, it is not but x minus 69 into bx by y minus 64. So, what is bxy? Bxy is equal to summation xy upon summation y squares. So, this is nothing but 39 by summation y square is 66. So, x minus 69 into 39 by 66 into y minus 64. If you simplify again further, so you will get in the format of y equal to alpha plus beta x. So, now here alpha and beta are very supporting factors. Beta is the slope of this particular line. So, beta is the real structure where it means it is the main regression coefficients, what we call it Vyx and Vxy. Alpha will just giving just you can say give you the indication where the line exactly starts. Let us take a case here. Whatever information we have, since we are going for y on x or x on y, then obviously the movement is like this. If we put it here x and y, then if we plot these you can all these points, then of course we get to know how is the set. Usually if we plot, then the structure will be this will be like this. Okay. So, now for every units, for every sample units 1, 2, 3, 4, 5 like this, then obviously there is a some y observations. So, now your movement will be like this. If you connect each and every point, then the movement will be like this. Okay. So, within the movements we like to know how is your path. That means this path is called as a line of the best fit. This is what we call it a y head equal to alpha head plus beta head x. This is the estimated equation which we derive from y into y bar equal to Byx into x minus x bars. The detailed calculation procedure we get to know when we go for the exact econometric modeling and regression modeling. We are not discussing about the detailed issue about the structure and setup. So, we are just briefing what is all about regression analysis. Once we will enter to this, you know, the structure of bivariate and you can say multivariate in a you can say research angle or you can say any practical problem angle, then obviously you can get to know how complexity is it and how it is derived really. So, structures. So, now we will summarize this entire concept, what is all about bivariate regression modeling, what is about the structure about variance, covariance, correlation, regression. So, the basic objective behind bivariate modeling is that we like to know what is the association between the two variables. So, that means the first condition is that in a particular system problem setup we must have two variables. This is first conditions, and for you know particularly covariance, correlation and regression, then the second important point is that both the variables have same number of observation. If one variable exceeds or you can say less than that of other variables, then obviously the structure is inconsistent and you cannot proceed further. So, now first condition is that you must have two variables in the systems and all the variables means both the variables have same number of observations. So, then we like to know what is the degree of association between the two variables. For that you can apply covariance, you can apply correlation, but correlation is better than covariance because it is unitless measurement, while covariance is not at all unitless measurement. So, obviously correlation is better choice than the covariance, although the calculation of correlation is a little bit complex. So, now if your objective is to know the degree of association between the two variables, then correlation is the best technique for that. However, if you like to know what is the cause and effect relationship between the two variables, then of course you have to go for regression analysis. So, regression analysis basically give you indication whether it is x influence y or y influence x. So, in that case we have two standard equations. For y on x, it is y minus y bar into Byx upon x minus x bar, and similarly for x on y, x minus x bar into Bxy upon y minus y bar. So, the issue is to know the regression coefficient, because it will give you indication how the path is all about, because the moment you will get regression coefficient Vyx and Vxy, then it will give you the indication of what is the value of correlation coefficient, the square of correlation coefficient, that is coefficient determinations, and that will give you the weightage of that particular relationships. If the value of that R square is very high and close to 1, then they are perfectly related to each other, or the degree of association is very high, and if it is very high, then obviously the prediction and forecasting structure is very reliable and also very easy. So, now the R will give you the indication about the movement between these two variables and their association, also its causality. So, now with this we have to end this particular class. So next class we will discuss detail about the basic statistic before you enter into the econometric modeling. So that is the case of probability and you can say hypothesis testing. So in the next lectures we will discuss the probability and hypothesis, then we will proceed to the multivariate econometric modeling. With this we will close this class. Thank you very much. Have a nice day.